Good day everyone, I'm Arhon Jay Zaragoza, electrical engineering student from ILOILO Science and Technology University. So for today's video, we are going to talk about microprocessor packaging. So first in line is we are going to talk about what is foundries and fabless. So foundries is a big semiconductor manufacturers that is responsible for chip fabrication. So example is Global Foundries, UMC, TSMC, the Intel, and the Texas Instrument. Next is the fabless. So it is small companies without fab. So it is responsible only for chip designing. So example is the Qualcomm, the AMD, the Broadcom, the Xilinx, and the famous NVIDIA. The next in line is we are going to talk about OSAT and the IDM. So OSAT is outsourced assembly and test. So it offers integrated circuit packaging services on the open market. So example of this is the Amcor technology and the JCET, and the next in line is the integrated device manufacturers. So semiconductor companies which design, manufactures, and sells integrated circuits, ICs, and products. So example is the IBM, Texas Instrument, and the Intel. Okay, so next is the pin through hole. So we have here the example of it is first is the dual line package, which is invented in 1964. So the IP comes in either plastic or ceramic version and have two rows of interconnects along opposite sides of the package. So packages are redundant. So both sides have pins, mostly have 64 pins, and next example is the single inline package, which is one line of leads with common pin. So this is the example of the DIP or the dual inline package, and this is the example of single inline package. Okay. Next in line is the surface mount technology, which is soldered directly on board, smaller than PETH, and easier and faster to assemble. And example of this is the QFP or the quad plate flat package. Here it is. Example of it. Mostly is as you can see, the Arduino. Arduino uses this kind of package. So it has quad pins. All sides of it has pins. And next example is the PGA or the pin grid array, which is here. Most of the CPUs right now uses it, like the AMD and the Intel. Next, the BGA or the ball grid array. So example of this is here. So ball grid arrays, mostly NVIDIA corporations are the makers of the famous GPU of RTX and GTX, use this kind of package. Okay, so this is the history of the microprocessors packaging. So we have here in in 1970s, the IPs was used, but in early 1980s, the invention of the surface mount technology was introduced. Until now, they used it. So next in line is the silicon interposer, which is defined as the silicon chip that can be used as a bridge or a conduit that allows electrical signals to pass through it and onto another element. So interposers are normally very frequently used in multi-die chips or boards. So the job of this interposer is to spread signals in a wider pitch and to take the connection to the different socket of the boards. Okay, so this is the example of interposer. So next in line is this type of interposer we have here is the passive and this active interposers. So active excuse me. So first is the passive. So passive has a higher wire density and cannot perform functions. So no active device in the substrates. So inactive interposers is just a fully functional chip embedded in the silicon substrate. So it has lower TSV density or the true silicon bias. So next in line is the structure of the interposer. So now this is the example, the three example. We have here the true silicon bias or the TSV, then the RDL or the redistribution layer, and the UBM or underbump metallization. So here DSV, it is a vertical pathway through the silicon interposer, and it is composed of mostly of copper pathways, silicon oxide isolator, and barrier, while RDL is the horizontal pathway. Okay, so it has copper lines each into silicon oxide layers and polish. So UBM is the pin pad connecting to the solder bumps and the copper in the RDL. So its material is nickel-based material. Next in line is the 2D and 3D packaging. So 2D introduces the silicon interposer and the through-silicon vias technology. So it integrates several electronic devices inside a single package by assembling them side by side, and the share base. The base and interposer provides connectivity, while the 3D is mounts two or more dies on top of each other, and it helps increase more functional density. So 3D. So today, the 3D packaging was used in this modern era of packaging, and is this has better performance than 2D packaging. Okay, we have there the interconnection techniques. We have here the wire bound, the flip chip, and the interposer. So here, wire bound has a low cost, while interposer is a high cost needs a high cost process of it, or you can buy it in a high cost. And here is the bandwidth. So interposers has the best bandwidth, and the chip size. The wire band is so big, and interposers are least have a least space, but a good transmitter of it has a good bandwidth. So in testing process, we need this. The testing process making in packaging is that they test this wire pull test, then die shear test, and post-process test where we're testing the temperature cycling and the X-ray inspection, then scanning acoustic microscopy of these microprocessors there. And we are also dealing with this electrical test for the capability and efficiency of this device. So this is from wafer to panel level packaging. So wafer to panel level packaging is it's the technology that of packaging the die while it is still on the wafer. So protective layers and electrical connections are added to the substrate before dicing. So originally, wafers were diced into individual chips, then packaged. Utilizing this W technology allows the chip continue to reduce in size, streamlines manufacturing, and provides easier way to test chip functionality. So we have here some example of this. We have the two types. Then we have the flow at the fan in and the fan out. So fan in is this one. So fan in is full packaging done on the wafer, resulting packaged in the same size as the die. Chip scale packaging, while the fan out WLP or the wafer is diced first, and it allows more inputs and outputs. Then package is bigger than die. Okay, so panel level packaging. So modern computers right now, CPUs, then the IC modules, basebands, Wi-Fi devices, and other network and server devices use this kind of packaging. So in comparison, panel level packaging now has the higher yield and even uses a low cost process. Then we have here it uses only fan out, and so it is quicker than this wafer level packaging. But the problem is that with the tools in WLP, the solder ball cracks easily. This is the problem, and the RDL issues and some production issues. When the panel is die shape, warp page, and the handling, so the fragile and sensitive to handle. Okay, that's it. Thank you. Have a good day.